My name is Sandor Brockhauser, and indeed, I'm the area coordinator for experiments in the Fermat project. And my role today is to dive deep into the NeXus data modeling. What is NeXus, and how can we use it for modeling our data in our experimental realm? It has already been mentioned that this is a 30-year-old standard. There is a standardization body, the NeXus International Advisory Committee, who is sitting together frequently and checks all the changes and proposals which are coming in. So then this standard can actually be live and can be able to cover all the needs of the community along these years and also hopefully in the future as well. 30 years ago, it was a European project which got started to be launched by NIST in the US, and it got funding and support from DOE and also continuous support from the EU as well. This is actually one of the reasons why we have chosen, because in the experimentary realm, in material science, there are already certain techniques which were covered by NeXus. And the key point here is how NeXus works is that it provides a semantic data annotation. We can define concepts in the NeXus definition language. Basically, we can build ontology. And this language, going back 30 years, it goes way beyond OWL, the web ontology language, has been established. Even before XML has been first published. NeXus has been adopted, the technologies, and the NXDL currently can be described in an XML format. There is a language description in an XML schema definition language in XSD, and all the definitions of the concept description should conform to this NXDL.XSD description. That's how we can verify if something is really properly written in that language. And as it has been mentioned, it started originally to cover experimental techniques from neutron, X-ray, and muon communities. But right now we are extending it also to material science, and lots of new techniques has been proposed to NeXus. Just a few weeks ago, we had the NIAC meeting in Grenoble, where we agreed that lots of proposals which we brought together from our material science community will be accepted, and in the next release will already contain these things. I also put www.nexusformat.org here to the bottom. You can go there and you can read more about NeXus and all the different definitions there. But the first question is, when we perform an experiment, what do we want to model? If we want to simplify the situation, in fact, we have observations where we collect data in a well-controlled environment. And the key point here is that when we store our experimental data, we have to always ensure that it can be properly interpreted. All the necessary metadata has to be provided with the data, with a proper explanation what that is, and what was its value, and why is it there, how did we perform the experiment itself. First, we always start with an idea of the experiment, and this we most of the time express in a physics model. Here we are using physics terms, that's what we call the experiment parameters, where we structure that in this experiment we will need slope, we will need car, and these are the different properties what we will need. These experiment parameters are connected to the physics model, and using already physics terms, that's how it becomes interoperable. And at that level, this is very easy and very good. We can use experiment parameters, which are physics concepts, to describe what and when needs to be set or maintained, measured or calculated during our experiments or afterwards in data analysis. But while this conceptual design model, it's using the physics model and its implementation independent, and so it's also interoperable, but it doesn't exactly tell how the experiment has been performed. What was the pressure in a chamber that can be part of the model, but how it has been produced and maintained, that's not covered. If we want to also describe these details, which is important for an experiment reproducibility, then we have to go deeper and we have to be implementation specific. It's not enough just to have a conceptual model. We have to have a technical design model. It's not anymore just the physics model, but also all the technical details. But our experiments are very complex. And each of these metadata elements can have lots of further detailed metadata elements which can explain what this number is, what are these properties, what is the meaning of these concepts there, what are the relationships between them, what are the jargons used in that experiment realm, which kind of calibration has been used in this experiment. This needs to be all stored. And if you go deeper and deeper, at one point you may ask yourself, well, how deep should we go for reproducibility? And indeed, it must be an agreement with the community how far we go, and then deeper, how I use my screwdriver. It's not anymore that important. We all know how to do that. But it's very important that there has to be an agreement in the community. Note that this agreement on a standard which the community will understand, it does not necessarily cover the needs of the local requirement of your lab. In your laboratory information management system or your electronic lab notebook, you may want to store information which might not is interesting for the global community, but can be important for your PhD students, how you actually work in your lab. And that's why the models what you may want to do in your NOMAD Oasis research data management platform may differ from what the community would need on a general level. And that's exactly what you can do in NOMAD. I've got the QR code here, so if you want, you can already use your phone and try to get it to go to the web page. Later, Chris Strom will drive you to how to use NOMAD, and this link you will need there, but you will get it actually later on as well. This slide has already been shown that we got the raw data, ENN, information data analysis, and in NOMAD you have a flexible system where custom data models can be put together, which covers all the needs of your laboratory. And if you have a community standardization, which, for example, expressed in the NeXus Standard, where you have the application definitions and base classes, Heiko Weber has already mentioned, this can be done, and NOMAD can take all these things directly into the research data management platforms, and you can use those concepts inside NOMAD seamlessly. So we've got this idea that we would like to model our experiments with all these concepts. And if we want to do it with a community, we need a controlled vocabulary so we all understand what is what. It has to be well defined what is the meanings of these different words. We have to define these concepts, and we also have to define their relationships, also the cardinality or optionality. For example, this experiment needed to have a slope, and a car was also needed to perform this experiment. Otherwise, this experiment wouldn't have worked. But there might be some optional elements in your experiment as well. You probably want to use standardized units. And if you have a community agreement, you express this in an agreed data format or in an API, then the community is ready to work with the data. You can start writing common tools and applications which can take the data and work with this. For this, we have chosen NeXus. As I have mentioned, there is an extendable data modeling language which can be actually expressed and it can cover all the needs what we need in material science, in the different experiment types in material science as well. From this description, there is a machinery which automatically generates HTML vocabulary for us humans, but also an whole ontology for machines. And NIAC is responsible for checking that this standardization will be in process. Whatever the community agreed on won't just disappear from one day to another. We may deprecate things, but things will be also available even in case of deprecation for a long time. NeXus is coming with lots of tools which enables verifications and validation. Ron Hildebrandt will speak about this in detail. And also visualization and exploration tools are also available, which we also support in the NOMAD platform. How does this modeling is done in NXDN, in the NeXus definition language? When we want to describe an experiment, and we write an application definition which describes what is this experiment about. When we do that, we are creating groups which are formed from so-called base classes, like experiment base class, car, or slope in this case. And these contains fields and attributes where you can also describe the units. They must come actually together with the units, and also uncertainties and other properties can also be then attached. Here are just a few examples of which kind of base classes you can have, which is already prepared. You don't have to think about. You can just take it, and in your application, you can reuse all the properties, what they have been already used and defined. And if you need, you can just specialize it further. You can inherit from this and continue working. This is the number of application definitions and base classes before our Fairmont project started. And I'm bringing this slide just to you how flexible the system is. In the last 2 years, to cover material science, we added 41 additional application definitions, so we more than doubled the number of experiment techniques defined, and lots of base classes also we included. To do that, we are using the NXDL language to describe all the different experimental techniques, and here I'm bringing NX ellipsometry. Here, as an example, it's listed among the contributed definitions, because whenever you bring a new technique, NeXus standardization body requires that this becomes as a new contribution in an incubation phase. And after agreeing with the community, then it can be actually become the standard. This is actually just what's happening with all the contributions, what we are now bringing to NeXus. We made these web pages as proposals, where all the definitions are described, like NX ellipsometry and all its details. And on the right-hand side, you can see that on these web pages, you can go there and you can annotate it. So the community can give feedback, can give suggestions, which we can then consider while we are developing it further. And when we have a consensus, then that final form, after agreeing with the whole of the community and our technology partners, then it becomes a standard in NeXus. Note that in NOMAD, we can already use these contributed definitions as well in the actual form, thanks to the flexibility of what NOMAD provides. But also afterwards, when it becomes standard, then it's a much more stable product, what we can use. All of the terms, all of the concepts of these vocabulary items are well registered, and there is a specific unique URL which points to the actual concept itself. Everything, as I mentioned, is expressed in XML, which we have actually found that it's a bit cumbersome to work with, especially when you want to add 200 definitions with all the relationships in between them. Manually editing, it's not that comfortable. So we ended up with the idea of doing it in YAML, where things are much, much easier. And this became already part of the standard. So if you go to the NeXus pages, NeXus can, already inside NeXus, you can convert from NXDL to XML to NYAML and vice versa. So you can actually do your work, do your manual work of adding new definitions in YAML format, where you just simply tell what is the name of the concept, and you can just write your documentation. It's really simple, and it works very quickly. So what we proposed for our communities is that let's work together in this YAML format, from where we got automatically generated HTML pages, which we can also annotate. This also converted to ontology. And here you can just see a screenshot from Protégé, where you can work with all these concepts and their relationships in the ontology world. And they are also automatically converted to concepts in NOMAD, what's called NOMAD meta info. So all these concepts are also available. When you take a NeXus file, some experimental data into NOMAD, then all the data and metadata can immediately properly connected. Important thing is that technology partners are involved in the process, because we're expecting that the instrument manufacturers will provide software which can then produce directly in this format. So then the files that are coming from the instruments can directly be dropped to NOMAD and other research data management platforms which are supporting the standard. Why do we speak about OWL and representation of our data in this web ontology language? It's because nowadays more and more interoperability between the different projects can be done on that layer using the semantic web. So we want to be compatible with this. We want to express all the NeXus vocabulary item and all the relationships between them. And we want to end with a situation where we can have all of our data sets represented in a knowledge graph. And we can then use reasoning on the full knowledge graph. And that means that you don't need anymore just specific software which can work and interpret your data, but the generic software will be able to interpret your data as well. Here, that means that generic tools will be able to do some data verification as well. And if you do that, then all the data expressed in the NeXus data format via the NeXus Ontology can be directly connected to the external world. And that's where we also see how much NeXus and NOMAD and the integration of NeXus and NOMAD can help us. Again, we have the ontology terms and concepts. If we are now speaking about the experiment, we can say that an experiment is nothing else, just a parameterized story of different elements, groups of an experiment type, an instrument, sample, calibration, and all of them has their own properties as it's described by the language. And they are all connected to individuals, to data objects, and that's how these concepts are explaining the data objects, and together with them, they are explaining the experiment itself, the whole of the experiment itself. Now, if we want to check an example, there was already example from photo emission. We will have examples from ellipsometry and Raman spectroscopy, all the different fields of optical spectroscopy. This example here shows the ontologic relationships of the different concepts for temperature-dependent IV measurements. What we see here is that if we have an temperature-dependent IV measurement, it has such an experiment has an entry, and this is actually the first point in the NeXus world. When you do something, then you've got an entry for this. In fact, this is inheriting, it's a specialization of a generic sensor scan entry. It has data, it has instrument descriptions, these are groups. It also has definition, and this is just a partial picture. There are lots of other things which I don't show here for clarity. And this is also inherited from the sensor scan definition, and this is actually a field. These are then connected to individuals. These are the actual data objects, which you can also connect in this ontology world to the concepts themselves. This is actually these purple lines here. And in between these objects, we've got the same relationships as also with the concepts themselves, in between the concepts themselves. So on the let's have a look last slide here. How does it work when we can start using it? Let's imagine we've got an individual, which is a definition. So in this data set, IV temp entry definition, it has this actual value, this string NX IV temp. And what we see from this, that this data set, NX IV temp entry definition, this is an individual of the type of an NX IV temp entry definition of this thing here. And in its definition, this is of a subset or subclass of something which has an actual value of only NX IV temp. The reason for this is because the definition of NX IV temp says that entry definition, it has an obligatory value of NX IV temp. So actually that's how it is. If we have this, actually we can see that we've got a consistent sub-data set, that this definition, this individual data object, it really, as it is expected, it is confirmed. But what happens if we are changing it? So we change the value of this individual, and it will become NX IV temp too. As we see, as humans, this is against the rule. And the nice thing is that you don't have to write any software which knows something about IV temp and how to perform temperature-dependent IV measurements, or a specific software which works only with NeXus Standard. Since we are using OVAL, the web ontology language, a very generic tools reasoner which works on this knowledge graph can immediately show that there is an inconsistency in the system, and the contradiction is automatically explained by this reasoner, which is simply finding automatically the facts, what I have just shown, that this data set definition, it has now the IV temp 2 value, but actually this IV temp entry definition, it should have only NX IV temp as a value, and this individual belongs to that group, so it's a type of this, so it should have this. And the reasoner is automatically explaining that something is going wrong. We had a data set which we are putting into NeXus, and using the NeXus Ontology, we can use a generic ontology tool which will understand what's going on, even find errors if there are any. With this, I give you a summary. The key point is that we are finding an efficient community standardization platform, that's NeXus. It provides an interoperable and reusable data exchange format, the NeXus files themselves. With the help of semantic web integration, we are open up to the world, and we can connect to other ontology descriptions. And a full support is available in NOMAD, which is a fair research data management platform and registered EOSC service, which we are then also supporting and developing it further. With this, the last slide collects a few links. Here, these are just red text, but we will provide the slides as well to you, and then you will be able to click on them, and you will be able to go and visit all these pages. With this, thank you very much. Thank you for your attention, and we can go to the next presentation where we go into the details to really do something hands-on and try it out. How does it work?